Hi Bobby,
Hi Aniruddhan.
what shall we do today?
So last class we concluded with common emitter.
That's right,
Wonderful.
because we had told them that we are going to give them something new that they have never seen before,
Correct.
and it ended up being this common emitter,
The first amplifier.
the first amplifier that they have seen. It was an inverting amplifier also.
Correct.
Correct. Shall we draw that circuit again?
Yes, that will be nice.
So I'll draw whatever we learnt in class.
Yes. So we have the biasing network.
Correct. I think this is what we learnt, and I think we call this VI, and we call this VO.
And the output signal was GM.
Correct. The output
RC
signal,
times.
so VO was minus, small VO and small VI are the signal.
Correct.
We have removed all DC components.
Correct.
Right? Was minus GM RC times VI. Correct. And this was our gain of the amplifier.
Yes. GM transconductance, we said it's IDC by VT.
That's correct. So if this bias current is, I think IEDC, I think the ICDC and IEDC were the numbers we used. So we said let it be some, let's call it IDC now. It's the same, no?
Yeah.
Maybe we'll just call it IDC.
Yes.
Easier. So we said that the GM of the transistor was just IDC over VT, the thermal voltage.
Yes.
Right? So in fact, it's interesting you asked me to write this. This is useful because if you want to get a particular gain, thermal voltage is always 26 millivolts.
Yeah.
You need to burn a certain amount of current, no? And power.
Correct.
We said that power is VCC times IDC. So you have to burn a certain amount of power to get the gain that you want.
Correct. So IDC actually kind of decides the value of GM. I mean, for a given
that is correct.
Transistor.
For a given transistor, yes, that's right.
So that means if IDC can be fixed, I'll also get very fixed GM.
That is true. Yes, that's right.
Oh, so that's why we have all this resistive network.
That is correct. To try to fix that IDC.
Okay.
I wonder if there is another way to fix IDC.
Yeah. Because you were mentioning that we may have further gain stages.
That is true.
Everywhere I will have to have this kind of resistive network to.
Correct. I know. So there must be some better way, no? So if you want the gain to be fixed, let us say RC, you get a very, very low tolerance resistor.
Correct.
Right? So now you need to fix IDC. And only problem with this is that you can fix RE. But VCC, you have to worry about. Ratio of R1 and R2 has to be fixed well.
Yeah.
Right? These two things we know. But we want to fix IDC even better. Because now it also depends on VBE of the transistor, for example. There may be slight variations. Okay.
So it's a current.
It's a current.
So why not?
Okay, that's true. I like your idea. I think I know what you mean.
Yeah.
You want to try to use a current source.
Current source. Yeah.
Okay, let's try it. So what I will do, I will make a copy of this here.
Yeah.
And maybe shall we try replacing, so I can try replacing RC, I need to replace either RC or RE with a current source.
Yeah.
Output is taken from collector.
Correct.
So let me fix the
Play with RE only.
RE only. I think the other one is too complicated. So shall I put a current source here?
Yeah.
So we'll call that IDC. Some I naught.
Yeah.
Shall we
Yes.
call it some I naught?
So it's a DC quantity.
It's a DC
DC
quantity. And now GM is now I naught by VT.
VT.
Okay. And I naught is fixed. No, it's a DC current source. It
And
is
the
fixed.
C, that serves the purpose again.
That serves the purpose again. We wanted VI to be equal to small VB,
Correct.
right? So that's what we wanted. That is why we added this.
Yeah. So C has to give a very low impedance, for
impedance.
the frequency of interest.
Correct. And I think that will still happen here because for DC, the capacitor will be open circuit.
Open.
Only the current source will be there.
Correct. Correct.
Right? And for AC, the current source becomes open circuited. We know this. DC current means there is no change in the current. For AC, it is like if you do superposition, we have seen this before.
Yes.
We have done superposition between DC and AC also sometimes. You will find that there is no AC current through I naught.
Correct. Correct.
And we wanted CE to be short circuit
Yes.
so that there is all the AC current flows through that.
Yes.
Perfect.
So once we have this I naught as a current source, still we will need R1, R2.
Okay. So let me copy this to the next page so that we can discuss that.
Yeah.
That's a very important point. So let us see. Suppose I take this. Well, this I naught current is there. I still need to find out what the DC voltage is at all the points.
Correct. Correct.
So in fact, I think I will need R1 and R2 because something needs to set the DC voltage at the base.
Yeah.
If you remove R1 and R2, it's
That
floating.
will be a floating point.
Correct. So you have to have it.
Okay. Okay.
Correct. So we need this.
Yes.
We need RC to set the DC voltage at the collector.
Yeah.
But now I have a question. What is the DC voltage at the emitter? Now that I have a current source, it's not so obvious to me.
Yeah. We can write in terms of VB maybe.
Okay, okay, correct. Okay, let's try that. So this is VB, no?
Yeah.
So we will just write it as VE DC will be VB DC minus VBE.
Yes.
So which is basically VB DC minus 0.7 volts.
Yeah.
Right?
Yeah.
Perfect. And in fact, this shows one difference, no, between having the resistor and having the current source. Because in this case, the DC current depended on RE.
Correct.
Here it's constant.
Yes.
So that is one big difference.
Yes. Yes.
That is one big difference. IDC is I naught independent of VEDC.
So maybe we should know how to realize I naught, or
Yes, I think we should. In fact, we have been talking about current source
yeah,
for a long time,
yes.
right?
We have solved many problems.
We have solved many problems also.
But,
so we need to,
yeah.
that is true. That
Yeah.
is true. So how would you do it? Okay. So, so what do we need? We need some current, current which is being drawn from the emitter in this case, but it could be from any node.
Yeah.
And from node, so shall we take the simple example?
Yeah.
I'll ground one end.
Correct.
That is the easy one to realize. So we want to realize this, no? From some node N, you want to pull out current.
Correct.
Well, let me suggest some easy thing. I can't use resistors, capacitors, inductors
to
realize a current source easily,
Yeah.
right? Not so easily,
Correct.
right? Otherwise, I have to use something. Oh, I know something that you can use. Technically, if I use an infinite inductor, no, and established a current I naught,
then it will be continuous.
then it will be continuous. The current cannot change because the current, but there is no concept of infinite inductance. We will leave that aside.
Yeah.
Right.
Also, that will affect our CE parallel.
CE parallel L.
Yeah.
Correct.
Yeah.
Right. And then next question is, how big is this infinite inductance? We don't want inductors normally, right?
Correct.
Unless you have the size that you can. Okay. So then next thing I looked at was a diode. And the diode, I applied some voltage, got some current. Right? It could supply any current you wanted.
Yeah.
But maybe the one thing that I could get is actually a transistor, maybe. Right?
So in the base emitter, when we give some voltage, you have a current coming through the
that is correct.
Collector.
That is correct. So maybe I will start with that circuit, no? That is what I was also thinking. So if I were to take this, no, and give some VBE, then I can get I naught.
Okay.
Only problem is I don't know what VBE to give. I have to find out the characteristics of the transistor, no?
Okay.
Because this I naught
so that means we may need some current to start with.
That is right. That's what it looks like, no? Because to do this, I naught equal, the dependence is exponential first of all. So we said it is some IS exponential VB by VT, no? Approximately.
Yeah.
Right? And first of all, it depends on IS.
Correct.
I take two transistors with different IS, I will need two different VBEs.
So suppose if I can pass some I naught through a transistor like this.
Yes.
And look at the base voltage of that.
Right. Then I can generate VBE somehow,
and give that to this.
And give that to this. Correct. Correct.
Even a diode junction may be.
Actually, even a diode junction will work. Because
the same equation.
The same equation. So in fact, that is the easiest way to do it, no? That is indeed the easiest way to do it. So that's what we should do. Okay. Except now I know what you're saying. You'll need a current to pass through the diode junction.
Correct.
Let us do that. That is one way to do it. So I will take one current source, I naught, and let us say we pass it through a diode junction. Right? That means that this voltage will be VD.
Correct.
That is VBE, no?
Yeah.
Because the equation is the same.
Correct.
So then what we can do, we can give this to your transistor. So now this current will be I naught.
Okay.
Yes. So now the student
that can be connected to
the common emitter amplifier. I'll show it in a different. Correct. To this point of the common emitter amplifier.
Okay.
But only one question.
How to
get that current?
So that can be even a resistor?
Exactly. I think to start with that can also be a resistor. Right? We don't need to use anything. We can in fact use a resistor and connect it to some known voltage.
Yeah.
Find out the value of the resistor and the voltage, which will give you the right current here.
Yes.
That is correct.
So actually you are kind of mirroring that current.
Correct. That is right. We are actually mirroring the current. That's right. So maybe what we'll do, we'll redraw it on the other page.
So ideally we need this transistor and that base emitter matched.
Correct.
Only then what we discussed will be correct.
That is correct. So that's why, so what I thought was, so suppose we draw this, no? So we can, so what you were saying was that this base emitter junction or it's a diode, but
Diode.
basically it's a junction.
Correct.
And this base emitter of this needs
Yeah.
to be matched.
Yes.
So maybe what we can do is this diode, no? Maybe we can realize it using a BJT.
Yeah.
Hmm?
And if they are made in same process,
In the same process, at the same time, same temperature,
matching will be
same doping levels, everything, matching will be good.
Yes.
Right? So you can actually realize this diode. So I'll draw it as a mirror so that it will be obvious.
Yeah.
Something like this.
Okay.
So you just connect the collector and the base together.
Ah.
So then the collector base junction is always zero biased. Base emitter junction will be forward biased depending on what current you put in.
So it's a diode.
It's a diode. It is a diode, right? Except now, suppose we call this Q1 and Q2, right? Q1 transistors Q1 and Q2 can be made such that they have the same IS1 and IS2.
Yeah.
Then you get exact mirroring of the current. So you'll get something like this. Maybe we'll just draw it,
Yeah.
redraw it with the true current mirror.
Correct.
Yeah. And now this can actually be connected to any circuit, no?
Yes.
So now we did it for a
C configuration.
CE configuration, but it can be connected to any circuit. In fact, we think back to all our circuits where we had a current source.
Yeah.
We can use this,
Yeah.
right? Inside those.
So if I have one more amplifier, I can mirror once again.
Mirror once again, good idea. Yes, yes indeed we can. So we can create one more mirror by taking the same base emitter voltage and connecting it to second one. So let us say this was Q1, Q2. Wait, maybe I'll move it a little bit.
For that we will draw separately.
We can draw separately.
Yeah.
So right now we'll just show this. So this is your current mirror.
Yes.
That we have promised.
Yeah.
This is your current mirrors.
Yes.
And now you are pointing out that you can do it once more.
Yes.
So what I will do, I'm going to cheat by making another copy of this. So I'll call this
Network 1 and
network
2.
1, network 2 and Q3.
Yeah.
And now all I need to do is take this and give it to the base of Q3 as well.
Yes.
So this is your VB1, that is equal to emitters are all grounded, the bases are all connected together. So that will be equal to VB2 and that will be equal to VB3.
Yes.
Right? In fact, now you can extend this.
Correct.
Now I can also do this, no? So this is one possibility. Suppose I do this. Suppose I take one more Q4. I can actually put two transistors in parallel. So Q4 and Q5.
So if you want to increase the current.
I want to increase the current. So what I will do like this. And I will connect all three terminals of Q4 and Q5 together. In fact, let me show that explicitly. Then what happens? This current will become 2 I0.
Yes, yes.
Right? So I could do this also. So this current mirror is a very useful circuit. I can make fractions of the current. I can make multiples of the current. I can do many
So
things.
you can mirror the way you want.
You can mirror the way you want.
Only assumption is we are assuming the base current is
That
zero.
is correct. You immediately caught the problem with this. Is that yes? If you do it too many times, then the base current could become a problem.
Yeah.
Because we are always assuming that beta is very large.
Yeah.
But if you have many of them, so now you need IB1, you need IB2,
Yeah.
you need IB3, you need IB4, you need IB5.
Yes.
If you do this too many times, all of that current is actually coming from here.
Yes.
Right? So I0 minus sigma IB is what will flow. That is what will create VBE. You will have an error. Maybe I'll call it IBI.
Yeah.
IBJ.
So the actual mirrored current is the current going through the
Collector or
collector of
emitter.
the first one.
That is correct. That is correct. So this is your error current.
Yeah, this is very nice.
Yeah. But if you just do it once or twice and beta is very large, you will not have any problem.
Correct.
Right? Unless you are building high precision circuits.
Yeah.
Right? For normal circuits, you can easily use this to bias your amplifier.
And even if there is an error, it's a fixed error.
That is correct. It's a fixed error.
Yeah.
That's right.
It's a systematic one.
It's a systematic. Correct. So now we even know how to design this current source also.
Yeah.
Yeah.